Nice having you again, my wonderful scholars. Jam Pass question 2001, question number 23. The diagram below shows two capacitors, P and Q, of capacitances, 2 microfarad and 4 microfarad, respectively connected to a DC source. The ratio of energy stored in P to Q is. Our question this time is centered on capacitance of a capacitor, or in the best way, the energy stored in the capacitor. Energy stored in a capacitor. Recall, capacitor is a circuit component. A circuit component that stores electrical energy in the form of electric field. Similar to an inductor, another circuit component that stores energy in magnetic field. That's an inductor. We are concerned with capacitor, which stores electrical energy in electric field. Recall, observe that the question is highly centered on energy stored in a capacitor. Any circuit component that stores energy must be halved. Recall, energy or work done is given as work done is force times distance. But that formula is in mechanics. It's not in electricity. We have to convert it to electricity. Work done in electricity becomes the force there changes to voltage, while the distance, what covers distance in electricity is charge. The charge is cover the distance times Q. For a better arrangement to be going this way, W is equal to QV. This is work done in a circuit, the formula for finding work done in a circuit. But if a circuit component has the ability to store energy, a capacitor stores energy in electric field. It's just like a reservoir, water reservoir. It stores electrical energy in electric field. Because of that storage, we'll be taking the average of the work done in the circuit. We'll divide by 2. Energy stored in electric circuits must be halved. So work done in a capacitor is half QV. Half QV. However, recall, capacitance is equal to Q over V. Capacitance of a capacitor is charge divided by voltage. Why am I making this emphasis? Because we can do manipulations of this energy or work done in a capacitor, energy stored in a capacitor. So let's see the simple manipulation I'm talking about. From the question, I'm only seeing capacitance and voltage. The unit of capacitance is microfarad or simply farad. Micro simply means 1 over 1 million. Micro, 1 over 1 million farad. However, the actual unit of capacitance is farad. So I'm seeing capacitances and voltage. I'm not seeing charge. Therefore, I'll do a simple manipulation. Let's make charge the subject. Charge becomes equal to CV. CV. Then I can now substitute. What do I do here? Work done in a capacitor, which can store. That's why I have half. Becomes half. The Q becomes CV. CV. There is another V here, making it V square. So this is the most suitable formula to solve this problem. We'll be taking this formula for finding energy stored in a capacitor to resolve the problem. So the formula we'll be using is W, work done in a capacitor or energy stored in a capacitor, is equal to half CV squared. So we've gotten our formula. Let's go back to the circuit diagram. Observe the diagram. Okay, observe the diagram. We are seeing parallel arrangement of capacitors. This is parallel connection. The current will divide or the charges will divide here. Anywhere our current or the charges will divide, that is parallel connection. Okay, then the question becomes, find the ratio of energy stored in P to Q. We're looking for ratio, and P comes first, while Q comes last. Then observe, In parallel connection, there is a theory you must know. The voltage at the source is the same in parallel connection. In parallel connection, the current changes, but the voltage remains the same. Please, let's take it again. In parallel connection, the current can change, but the voltage is constant. What does that mean? The voltage here is the same as the voltage there and the same as the voltage there. So voltage is the same in parallel connection. Why the current is not the same? The current can divide, but the voltage cannot divide. That means whatever thing we have here is the voltage here, likewise the voltage there. Then recall, we're looking for energy stored in P. Capacitor P is to energy stored in capacitor Q. Then let's forge ahead. Then we say that the energy is half CV squared. You'll be having half times the capacitance of P is 2 microfarad times, okay, let's create a bigger space. Okay, coming over here, energy stored in capacitor P is to energy stored in capacitor Q. Capacitor P, we're having half times the capacitance there, 2 microfarad, times the voltage there. This V is the same for all of them. They're in parallel connection. V squared is to, we'll go back to energy stored in Q, half times 4 microfarad times V squared. Voltage is the same. Then we'll push ahead. Then let's continue. So this is like division. This is like division. You should know that half divided by half, they will cancel. They will cancel. Is 2 is ratio or division. 2 key itself, 1. 2 key here, 2. Micro will cancel micro. Farad, farad, off. Then we'll continue. What is remaining here now is the WP now is to WQ. What remains is, this is 1 times B squared. What remains there is B squared. Whereas what remains there is 2V squared. 2V squared. 1 times 2 times V squared. 2V squared. Then we can push ahead. V squared cancels V squared because they are the same. The voltage is the same in parallel connection. So we're having 1 is to 2. 1 is to 2. 1 is to 2. Okay. So going to our option. The energy stored in P. The ratio of energy stored in P to energy stored in Q is 1 is to 2. That simply means that we have more energy in Q compared to what? P. The energy in P, if the energy in P is 5, therefore the energy in Q will be 2 times 5, making it what? 10. Q is 2 times greater than P. Okay, from the option, the best option there is option D. Thank you. Please stay tuned as we push ahead.